In the quiet of a clear night sky, Jupiter glows, bright, serene, and timeless. Its surface, a mesmerizing blend of amber and cream, is a dance of ammonia and methane clouds spanning over 86,881 miles, more than 11 times Earth's width. Beneath this calm exterior, storms like the Great Red Spot, a hurricane-like vortex raging for at least 350 years, churn with winds reaching 400 miles per hour, driven by Jupiter's rapid 10-hour rotation. At its core lies a mysterious region of intense pressure and temperature, possibly liquid metallic hydrogen, generating Jupiter's immense magnetic field, 14 times stronger than Earth's. If you feel that same tension, that pull toward something we're not supposed to see, hit like, subscribe, and comment your thoughts. And if you want others to join us on this journey, share the video, X, Facebook, Reddit, anywhere you can. You're the reason stories like this reach beyond the algorithm. Thank you for being awake. For billions of years, Jupiter has shaped the solar system with its powerful gravitational pull and magnetic field, creating dazzling auroras at its poles as charged particles interact with the atmosphere. To unveil its mysteries, humanity sent the Juno spacecraft, launched in 2011, which traveled 1.7 billion miles to reach Jupiter. On July 4, 2016, Juno entered Jupiter's orbit, beginning a series of close flybys within 100 miles of the planet's cloud tops, closer than any previous mission. Juno's discoveries have challenged theories about planet formation and evolution. Its data, images of storms revealing their depth and structure, magnetic field measurements suggesting complex internal dynamics, and evidence of a possibly liquid core, have sparked new questions. As Juno continues its 53-day orbit, it reveals secrets of the solar system, including the string of pearls, massive cyclones at Jupiter's poles, each larger than the United States. These observations reshape our understanding of Jupiter and offer clues about the formation of gas giants and the birth of Earth. Part 1. The Giant Awakens. What if the most familiar object in our night sky is the least understood? Jupiter, visible to humanity for millennia, remains an enigma. Its vast size, over the 300 Earths could fit inside it, has long captured our imagination. Yet, its true nature eludes us. NASA's Juno spacecraft, arriving in 2016, began to reveal the gas giant's secrets. Beneath its serene cloud bands lies a realm of chaos, storms defying planetary behavior, winds exceeding 400 miles per hour, and a core that challenges formation theories. The Great Red Spot, a storm raging for over 350 years, is shrinking by roughly 930 kilometers in diameter per year. Why it persists remains a mystery. This storm is so large that Earth could fit inside its boundaries. Beyond it, Jupiter's atmosphere is a battleground of competing storms, driven by intense heat and pressure. These storms extend deep into the planet, with dynamics likened to turbulent flows in a boiling pot. Lightning on Jupiter, detected by Juno, is not only more powerful than Earth's, but also behaves differently, flashing at rates that defy conventional understanding. Juno's mission was to unravel Jupiter's enigmas. Launched in 2011, it carried 9 instruments to map the gas giant's depths, including a microwave radiometer to peer through the thick clouds and a magnetometer to study the magnetic field. What it found was a world of hidden storms, magnetic anomalies, and a core that rewrites planetary science. Jupiter's magnetic field is the most powerful in the solar system, stretching over 24 million kilometers, large enough to envelop the orbit of the Moon if centered on Earth. It traps charged particles, creating intense radiation belts that glow with eerie auroras. Juno, built to withstand this environment, carries a titanium vault to shield its electronics, a protective measure that ensures its delicate instruments survive the onslaught of radiation. Its solar panels, though massive, will degrade over time due to these harsh conditions, slowly losing efficiency as the mission progresses. Juno discovered that Jupiter's magnetic field is offset and tilted, creating a lopsided magnetosphere with chaotic auroras. These auroras, fueled by Jupiter's rapid 9.9-hour rotation, are the most spectacular light show in the solar system. They shimmer in ultraviolet and infrared wavelengths, invisible to human eyes but detectable by Juno's instruments. The auroras are not merely decorative, they hint at the complex interplay between Jupiter's magnetic field and the solar wind, a dance of cosmic forces. Observation: Jupiter's interior is not a uniform mix of hydrogen and helium. Juno's gravity measurements revealed a core of heavy elements, 10 to 30 times Earth's mass, but diffuse and gradually diluting into the surrounding hydrogen and helium. This challenges traditional planetary formation models, which often assume a more distinct and compact core. Interpretation: the fuzzy core suggests Jupiter formed through chaotic collisions and mixing of materials. This could mean the planet accreted from catastrophic mergers of larger planetary embryos, explaining the diffuse nature of the core. Such a violent origin story would have released tremendous energy, reshaping the young Jupiter and leaving behind a legacy of turbulence still visible today. Speculation: if Jupiter's core resulted from violent mergers, it raises questions about the early solar system. Did similar events shape Saturn, Uranus, and Neptune? Future missions may provide answers, building on Juno's discoveries. The upcoming Europa Clipper, for example, will explore Jupiter's icy moon, Europa, a world thought to harbor a subsurface ocean and potentially life. Juno's findings about Jupiter's magnetic field and internal dynamics may offer clues about how Europa's environment evolved. To understand Juno's secrets, we must look back at its beginning. The spacecraft features 3 solar panels, each over 9 meters long, covered in 18,000 solar cells. Despite low sunlight at Jupiter's distance, roughly 5% the intensity of sunlight on Earth, these panels generate enough energy to operate Juno's instruments and communicate with Earth. This engineering feat ensures that Juno can continue its mission even as its solar cells slowly degrade in the harsh radiation environment. To reach Jupiter, Juno traveled over 2.8 billion kilometers, including a gravity assist from Earth in 2013. This flyby boosted its speed, ensuring timely arrival. Upon reaching Jupiter in 2016, Juno executed a daring orbital insertion, placing it in a highly elliptical orbit. This trajectory allows Juno to approach within 4,200 kilometers of Jupiter's cloud tops at its closest point, collecting detailed data on the planet's interior and atmosphere. At its farthest point, Juno extends to a distance of 8.1 million kilometers, providing a broader view of the gas giant's magnetosphere. Since then, Juno has completed over 50 orbits, each lasting 53 days. It dives deep into Jupiter's gravitational field, gathering data on the planet's interior, magnetic field, and atmospheric dynamics. As Juno continues its mission, it paves the way for future explorations of the outer solar system, inspiring scientists to unravel the secrets of the cosmos. Its discoveries are not just about Jupiter. They offer insights into the formation of planets, the behavior of gas giants, and the fundamental processes that govern our solar system. Part 2. The Spacecraft and the Storm. Could a spacecraft built on Earth survive the fury of Jupiter? Juno was born out of necessity, a necessity to see what no telescope or previous mission could. Constructed at Lockheed Martin's facilities in Denver, Colorado, the spacecraft was a marvel of engineering. Its hexagonal body and 3 massive solar arrays, each nearly 30 feet long, gave it the appearance of a cosmic windmill. But its design was more than aesthetic. It was a solution to a daunting challenge. Jupiter, 5 times farther from the Sun than Earth, receives only 4% of the sunlight we do. To generate enough power, Juno's solar panels had to be the largest ever built for a deep space mission. Spanning over 600 square feet, these panels were meticulously engineered to capture every available photon, ensuring the spacecraft could operate even in the dim light of Jupiter's orbit. The solar arrays were not just large, they were also remarkably efficient. Made of over 18,000 solar cells, they were designed to produce about 500 watts of power at Jupiter, roughly equivalent to the energy used by 5 standard light bulbs. This modest output was enough to power Juno's instruments and systems, but it required careful management. Engineers developed sophisticated power-saving protocols, cycling instruments on and off to conserve energy while maximizing data collection. Despite these constraints, Juno's solar arrays proved their worth, setting a precedent for future missions to the outer solar system. Yet, power was only the beginning of Juno's challenges. Jupiter's magnetic field is the most intense in the solar system, trapping charged particles and creating radiation belts that would destroy unshielded electronics in minutes. To protect its sensitive instruments, Juno carried a 400-pound titanium vault, an armored box that housed its most critical systems. This vault, with walls nearly a centimeter thick, was designed to withstand the equivalent of 100 million dental X-rays worth of radiation. Even with this shielding, the spacecraft's lifespan was limited. Eventually, the radiation would win, slowly degrading Juno's systems over time. The radiation wasn't the only threat. Jupiter's powerful magnetic field also generated intense electrical currents that could disrupt Juno's electronics. To mitigate this, engineers incorporated specialized shielding and redundant systems, ensuring that the spacecraft could continue operating even if some components failed. This attention to detail extended to every aspect of Juno's design. For instance, its communication system was built to withstand not only radiation, but also the extreme temperatures of space, which could fluctuate between 150 degrees C and 100 degrees C, as the spacecraft moved in and out of sunlight. But Juno was not just a survivor, it was an explorer. Its 9 scientific instruments were designed to probe every aspect of Jupiter, from its magnetic field to its atmospheric composition. Among them was JunoCam, a visible light camera that allowed the public to share in the mission's discoveries. Though not a primary science instrument, JunoCam captured breathtaking images of Jupiter's swirling clouds and storms, inspiring millions around the world. Its high-resolution photographs revealed intricate details of the planet's weather patterns, including the iconic Great Red Spot, a storm larger than Earth that has raged for centuries. Another key instrument was the microwave radiometer, a tool that would revolutionize our understanding of the planet's interior by measuring water and ammonia deep within its atmosphere. This instrument was capable of peering through Jupiter's thick cloud layers, mapping the distribution of these critical compounds with unprecedented precision. By studying the abundance and distribution of water, scientists hoped to unravel the mysteries of Jupiter's formation. Did the planet form in its current location, or did it migrate from elsewhere in the solar system? The answers could reshape our understanding of planetary evolution. Juno's magnetometers were equally pivotal. These instruments were tasked with mapping Jupiter's magnetic field, which is not only the strongest in the solar system, but also one of the most complex. By studying its fluctuations in structure, researchers aimed to uncover the mechanics of the planet's dynamo, the churning liquid metallic hydrogen deep within its core that generates the magnetic field. This, in turn, could provide insights into the internal workings of gas giants and the conditions that might exist on exoplanets beyond our solar system. With its instruments ready and its solar arrays deployed, Juno was poised to embark on one of the most ambitious missions in the history of planetary exploration. But first, it had to reach its destination, a journey that would test the limits of human ingenuity and the resilience of the spacecraft itself. Launched on August 5, 2011, Juno began a 5-year trek through the solar system, covering a distance of nearly 1.7 billion miles. Its trajectory was carefully calculated to take advantage of gravitational assists, including a flyby of Earth in 2013 that boosted its speed and adjusted its course toward Jupiter. The journey was not without risks. Juno had to navigate the asteroid belt, a region filled with debris that could have destroyed the spacecraft if struck at high speeds. Mission controllers monitored its progress closely, ready to adjust its course if necessary. The spacecraft also had to endure extreme temperatures in the vacuum of space, which could have caused materials to degrade or fail over time. To mitigate these risks, engineers used specialized coatings and insulation to protect Juno's components, ensuring they could withstand the harsh conditions of deep space. On July 4, 2016, Juno finally arrived at Jupiter. Its approach was fraught with danger. The spacecraft had to thread a needle, firing its main engine for 35 minutes to slow down enough to be captured by Jupiter's gravity. Any miscalculation or equipment failure could have sent Juno careening into the planet or flung it into the void of space. But the maneuver was executed flawlessly, and Juno settled into a highly elliptical orbit around the gas giant, ready to begin its groundbreaking mission of discovery. Observation. Juno's arrival at Jupiter marked a triumph of engineering and human achievement. The spacecraft's design, from its massive solar arrays to its titanium radiation vault, exemplified the ingenuity required to explore the outer reaches of the solar system. Its instruments, including JunoCam and the microwave radiometer, offered unprecedented insights into Jupiter's complex environment, paving the way for future missions to gas giants and beyond. Interpretation. The success of Juno's mission demonstrated the feasibility of solar-powered exploration in the outer solar system. By overcoming the challenges of low sunlight and intense radiation, Juno set a precedent for future spacecraft, inspiring new technologies and approaches to deep space exploration. Its discoveries also deepened our understanding of Jupiter's formation and internal dynamics, providing clues about the origins of the solar system and the conditions that might exist on distant exoplanets. 8th, speculation. As Juno's mission continues, it raises new questions about the nature of gas giants and their role in planetary systems. Could Jupiter-like planets in other star systems harbor similar dynamics, shaping the evolution of their solar systems? And what might future missions uncover about the mysterious processes at work within these colossal worlds? The answers could redefine our place in the cosmos and our understanding of the universe itself. Part 3. The Long Journey. How do you send a spacecraft to the outer reaches of the solar system? The answer lies in a delicate dance of physics, timing, and human ingenuity. The journey to Jupiter is not just a matter of pointing a spacecraft in the right direction and hitting launch. It requires harnessing the forces of gravity, momentum, and the vast emptiness of space itself. For Juno, this journey would span nearly 5 years and cover over 1.7 billion miles, pushing the boundaries of what humanity can achieve in the cosmos. The path to Jupiter is not a straight line. Launched aboard an Atlas V rocket on August 5, 2011, Juno began its journey by traveling outward past the orbit of Mars. But then, in a maneuver that defied intuition, it turned around and headed back toward Earth. This was not a mistake. It was a calculated strategy, a testament to the ingenuity of mission planners. In October 2013, Juno performed a gravity assist, using Earth's pull to accelerate itself like a cosmic slingshot. The maneuver added over 16,000 miles per hour to its velocity, exactly what it needed to escape the inner solar system and reach its target. This slingshot effect is not just a clever trick, it is a necessity. Without it, Juno would have required a much larger, more powerful rocket to reach Jupiter, increasing the mission's cost and complexity. As it stood, the Atlas V, with its 860,000-pound thrust, was just enough to get Juno on its way, but the gravity assist provided the critical boost needed to reach the outer solar system. For the next 3 years, Juno coasted through the void of deep space. Its systems were mostly dormant, preserving power as its solar arrays turned toward the distant sun. The spacecraft was designed to operate at extreme distances from the sun, where sunlight is 25 times fainter than it is at Earth. Juno's 3 massive solar arrays, each the size of a tractor-trailer, were specifically engineered to capture enough light to power the spacecraft in these dim conditions. Despite the harsh environment, Juno's instruments remained largely silent during this period, conserving energy for the trials ahead. But on July 4, 2016, the spacecraft awoke. Arriving at Jupiter, it faced its greatest challenge yet, entering orbit around the gas giant. Traveling at over 165,000 miles per hour, Juno had just one chance to slow down and be captured by Jupiter's gravity. A 35-minute engine burn, executed autonomously, would determine the fate of the mission. At 11:18 p.m. Eastern Time, the burn began. Mission Control watched as telemetry trickled in from nearly 500 million miles away. The signal, traveling at the speed of light, took 48 minutes to reach Earth, a humbling reminder of the vast distances involved. 35 minutes later, confirmation arrived. Juno was in orbit. The spacecraft had arrived within 1 second of its predicted timing, a testament to the precision of its design and the skill of its engineers. This achievement was made possible by years of meticulous planning and testing. Every component of Juno, from its titanium vault shielding its electronics to its Laros 1B main engine, was designed to operate flawlessly in one of the harshest environments in the solar system. But the true test was yet to come. Juno's orbit was unlike any other, carrying it high above Jupiter's north pole and then plunging it down between the planet and its radiation belts. This 53-day orbit was carefully chosen to minimize exposure to Jupiter's intense radiation, which is strong enough to fry unprotected electronics in minutes. From this vantage point, the spacecraft could peer directly at regions of Jupiter that had never been seen up close, and what it saw would change everything. The first images sent back by Juno revealed storms the size of Earth, swirling in chaotic patterns across the planet's surface. The Great Red Spot, a storm larger than our entire planet, was captured in unprecedented detail, its towering clouds casting shadows on the layers below. Observation: Jupiter's auroras, visible as ethereal curtains of light, were found to be far more complex than previously thought. Juno's instruments detected powerful electrical currents flowing between the planet and its magnetosphere, generating the most intense auroras in the solar system. These observations challenged existing models of how auroras form, suggesting that Jupiter's magnetic field plays a far more active role than scientists had imagined. Interpretation: the data from Juno's initial orbits indicated that Jupiter's interior is not a uniform layer of hydrogen and helium, as once believed. Instead, the planet appears to have a complex structure with layers of metallic hydrogen and possibly even a rocky core. This discovery has profound implications for our understanding of how giant planets form and evolve. It suggests that Jupiter, once thought to be a relatively simple gas giant, is actually a dynamic and layered world, with processes occurring deep within its interior that shape its surface and atmosphere. Speculation: if Jupiter's interior is indeed as complex as Juno's data suggests, it raises intriguing questions about the origins of the solar system. Did Jupiter form in its current location, or did it migrate inward from the outer reaches of the system? Could the rocky core at its center be a remnant of the primordial material that formed the Sun and planets? And what does this mean for the countless exoplanets we have discovered orbiting distant stars? Juno's journey is far from over, but its discoveries have already rewritten the textbooks on the largest planet in our solar system. As it continues to orbit Jupiter, diving deeper into its mysteries, it will undoubtedly reveal even more about the nature of the cosmos and our place within it. Part 4. The polar enigma. What if the poles of Jupiter are stranger than its equator? On August 27, 2016, Juno completed its first science pass, transmitting images that left scientists stunned. Jupiter's North Pole was not the orderly realm of bands and zones visible from Earth. Instead, it was a chaotic, swirling mass of cyclones, packed together in geometric patterns that defied explanation. At the center sat one massive storm, roughly 4,000 kilometers in diameter, surrounded by 8 smaller cyclones, arranged in a near-perfect octagon. Each storm was larger than Earth, yet they remained locked in formation, neither merging nor drifting, as if governed by an unseen force. The largest of these cyclones alone could swallow the entire Atlantic Ocean, its winds roaring at speeds exceeding 360 kilometers per hour. The stability of these storms was almost incomprehensible. On Earth, cyclones are transient, forming over warm ocean waters and dissipating within days or weeks as they encounter land or cooler temperatures. Yet on Jupiter, these colossal storms seem to defy the rules of nature, maintaining their structure and position for years, possibly decades. The energy driving these storms was immense, comparable to the total solar radiation absorbed by Earth in a single day. But unlike Earth's weather systems, which are powered by the sun, Jupiter's polar cyclones drew their energy from the planet's internal heat, a remnant of its formation 4 billion years ago. At the South Pole, the pattern was different but equally strange. 5 cyclones surrounded a central vortex, forming a pentagon. These storms, too, were stable, their spiral arms smashing together without combining. The central cyclone alone spanned over 6,000 kilometers, its towering clouds casting shadows that stretched for hundreds of kilometers. Each of the 5 surrounding cyclones was roughly the size of Mars, their edges grinding against one another in a perpetual dance of wind and pressure. The interactions between these storms generated lightning strikes hundreds of times more powerful than those on Earth, illuminating the polar night with brilliant flashes of energy. The discovery was unprecedented. Scientists had expected Jupiter's poles to resemble the banded structures seen at lower latitudes, where the Great Red Spot and other oval storms drifted freely. Instead, they found a realm of rigid symmetry, where storms behaved more like cogs in a cosmic machine than chaotic weather systems. The geometric precision of the cyclones suggested an underlying mechanism, perhaps a deep atmospheric wave or magnetic interaction that kept them in place. However, no existing theory could fully explain the phenomenon. Observation. The polar cyclones appeared to be anchored at specific latitudes, suggesting a connection to Jupiter's magnetic field or internal structure. Their positions aligned almost perfectly with regions where the magnetic field was strongest, hinting at a possible electromagnetic influence. Speculation. Some researchers proposed that the cyclones might be pinned to magnetic hotspots created by the planet's dynamo, a swirling core of liquid metallic hydrogen. Others suggested that atmospheric waves, driven by the planet's rapid rotation, could create zones of stability that trap the storms in place. But without more data, these ideas remained speculative. As Juno continued its orbits, it revealed more about the polar enigma. The spacecraft's microwave radiometer, MWR instrument, peered beneath the cloud tops, mapping the temperature and composition of the atmosphere down to 350 kilometers below the surface. The results were astonishing. The polar cyclones extended deep into the atmosphere, their roots reaching down to pressures equivalent to those found in Earth's lower stratosphere. This depth suggested that the storms were not mere surface phenomena, but tapped into the planet's vast internal energy reservoir. The MWR data also revealed another surprise. The polar atmosphere was surprisingly dry. Unlike the equatorial regions where ammonia and water vapor were abundant, the poles were depleted of these compounds. This aridity may have contributed to the stability of the cyclones, as the lack of moisture reduced the likelihood of convection and storm merging. However, the cause of this polar dryness remained a mystery, adding another layer of complexity to the enigma. The polar cyclones were just the beginning of Juno's revelations. As the spacecraft continued its orbits, it would uncover even more mysteries hidden beneath Jupiter's clouds, mysteries that would force scientists to rethink everything they knew about the gas giant and its place in the solar system. With each pass, Juno's instruments probed deeper, revealing a world of swirling storms, powerful magnetic fields, and an interior that seemed to defy the laws of physics. The journey to understand Jupiter's poles had only just begun, but it promised to rewrite the textbooks and challenge our understanding of planetary science. Part 5. The Magnetic Labyrinth. What if Jupiter's magnetic field is more complex than we ever imagined? Jupiter's magnetic field has long been known to be powerful, but Juno's magnetometer revealed just how strange it truly is. Most planets with magnetic fields generate them through a process called a dynamo. On Earth, liquid iron in the outer core flows, creating electric currents that produce a magnetic field extending into space. Jupiter, however, is different. Its dynamo is fueled not by molten iron, but by metallic hydrogen, compressed so intensely by the planet's immense pressure that its electrons break free and flow like a metal. This metallic hydrogen layer, buried beneath a mantle of molecular hydrogen, is thought to span a staggering 90% of Jupiter's radius, generating a magnetic field roughly 20,000 times stronger than Earth's. Scientists expected Jupiter's magnetic field to be strong, but relatively simple. A clean dipole like Earth's, just much larger. What Juno found was anything but simple. The magnetic field was lopsided, far stronger in the northern hemisphere than in the southern. Scattered across the planet's surface were patches of intense magnetism that defied any simple model. One of these patches, near the equator, became known as the Great Blue Spot, a region of exceptionally strong magnetic flux that moved eastward, pushed by winds that extended thousands of miles deep. This spot, though invisible to the naked eye, was larger than Earth itself, a silent storm of magnetism racing through the planet's interior at speeds exceeding 300 kilometers per hour. The Great Blue Spot was not the only anomaly. Juno's data showed that Jupiter's magnetic field was changing over time, a phenomenon known as secular variation. Before Juno, scientists had only ever confirmed secular variation on Earth. Now, they were seeing it on Jupiter, and the changes were tiny, detectable only through decades of data. These shifts in the magnetic field were subtle but significant, hinting at deep unseen processes churning beneath the planet's cloud tops. Some of these changes were as small as 100 nanoteslas per year, yet they spoke volumes about the restless nature of Jupiter's interior. But why was the magnetic field so complex? The answer, scientists suspected, lay deep within Jupiter's interior, a realm of pressure and temperature so extreme that it defied human imagination. At depths where the pressure reaches over 40 million times that of Earth's atmosphere, hydrogen transforms into a metallic state, conducting electricity and generating the planet's powerful magnetic field. This region, known as the dynamo layer, is thought to be turbulent and dynamic, with swirling currents of metallic hydrogen creating complex magnetic patterns that ripple outward. These currents are not uniform. They twist and turn, driven by the planet's rapid rotation, which completes a full cycle every 9.9 hours. Observation. The complexity of Jupiter's magnetic field suggests that its dynamo is not a single coherent system, but a collection of smaller, interacting dynamos. These smaller dynamos could be influenced by local variations in temperature, pressure, and composition within the metallic hydrogen layer. The Great Blue Spot, for example, might be the surface expression of a particularly strong local dynamo, a hotspot of magnetic activity driven by intense convection currents deep below. Speculation. If Jupiter's magnetic field is indeed the result of multiple interacting dynamos, it raises intriguing questions about the planet's interior structure. Could the metallic hydrogen layer be more heterogeneous than previously thought, with regions of differing composition or temperature? Might these variations be linked to the planet's formation history, preserving echoes of ancient impacts or accretion events? The answers to these questions could rewrite our understanding of how gas giants form and evolve. The magnetic field's complexity also has consequences for Jupiter's environment. The planet's powerful magnetosphere traps charged particles from the Sun, creating intense radiation belts that glow with auroras far brighter than those on Earth. Juno's observations revealed that these auroras are not confined to the polar regions, but extend far toward the equator, forming intricate patterns that shift and pulse with the magnetic field's fluctuations. These auroras are not just beautiful. They are a window into the unseen processes deep within Jupiter, a visual manifestation of the planet's magnetic labyrinth. One of the most striking discoveries was the realization that Jupiter's magnetic field is not a static structure, but a dynamic, ever-changing entity. As Juno orbited the planet, its instruments detected sudden bursts of magnetic activity, which scientists dubbed magnetic storms. These storms, though brief, were intense, releasing energy equivalent to millions of lightning strikes on Earth. They seemed to originate deep within the planet and propagate outward, disrupting the magnetosphere and sending shock waves through the charged particles trapped within it. Interpretation: the magnetic storms observed by Juno may be evidence of instabilities within Jupiter's dynamo layer. As currents of metallic hydrogen shift and interact, they could create temporary imbalances that release energy in violent bursts. These storms might also be influenced by external factors, such as solar wind pressure or interactions with Jupiter's moons, particularly Io, which is volcanically active and contributes a significant amount of material to the magnetosphere. The implications of these findings extend far beyond Jupiter itself. Understanding the intricacies of the planet's magnetic field could shed light on the behavior of other gas giants, such as Saturn, Uranus, and Neptune, each of which has its own unique magnetic characteristics. It could also inform our understanding of exoplanets, many of which are likely to have magnetic fields of their own. By unraveling the mysteries of Jupiter's magnetic labyrinth, we gain insight into the fundamental processes that shape planets across the universe. In the end, Jupiter's magnetic field is not just a curiosity, it is a testament to the planet's living, breathing interior. Every twist and turn of its magnetic lines, every burst of energy, and every shifting aurora tells a story of a world in motion, a world shaped by forces so vast and powerful that they challenge the limits of human comprehension. And as Juno continues its journey, the story of Jupiter's magnetic labyrinth grows ever more intricate, inviting us to explore further, to question deeper, and to marvel at the wonders hidden beneath the clouds. Part 6. The Depths of the Gas Giant. How deep do Jupiter's winds go? Juno's orbit was designed not just to map Jupiter's magnetic field, but to probe its interior. By measuring how the planet's gravity tugged on the spacecraft, scientists could reconstruct how mass was distributed beneath the clouds. The data revealed something unexpected. Jupiter's winds, which reach speeds of over 400 miles per hour at the surface, penetrate far deeper than anyone had imagined. These winds are not mere surface phenomena, but integral parts of the planet's dynamism. The depth of these winds means that the atmospheric bands we observe are not superficial features, but are rooted in the planet's deep structure, influencing its internal dynamics in profound ways. In fact, these winds extend more than 1,900 miles deep, reaching all the way down to where hydrogen transitions into its metallic form. This layer, known as the metallic hydrogen envelope, is one of the most exotic and poorly understood environments in the solar system. At this depth, the pressure is so immense, millions of times greater than Earth's atmospheric pressure, that hydrogen loses its gaseous properties and behaves like a liquid metal. This metallic hydrogen is believed to be a key component in generating Jupiter's powerful magnetic field, which is 20,000 times stronger than Earth's. The interaction between the deep winds and this metallic layer could explain why Jupiter's magnetic field is so complex and dynamic, with auroras that dwarf anything seen on Earth. This discovery reshaped our understanding of how gas giants work. Jupiter is not just a ball of gas with weather on top, it is a dynamic system where atmospheric flows interact with deeper layers in ways we are only beginning to understand. The winds themselves are thought to be driven by the planet's internal heat, which is roughly equal to the amount of energy it receives from the sun. This internal heat is a remnant of Jupiter's formation process, and it continues to power the planet's weather systems, creating a self-sustaining cycle of energy and motion. But the winds were not the only surprise lurking in Jupiter's depths. As Juno's gravity measurements revealed, the planet's core was not what scientists expected. For decades, two competing theories had dominated the debate about Jupiter's interior. The first suggested that the planet formed through gravitational collapse, with gas pulling itself together under its own weight. In this model, Jupiter would have no core at all, just layers of hydrogen and helium stacked endlessly toward the center. This theory was compelling because it could explain the rapid formation of gas giants in the early solar system when the disk of gas and dust around the sun was still dense enough to allow such a process. The second theory, core accretion, proposed that Jupiter started with a solid nucleus made of rock and ice, which then pulled in surrounding gas to form the giant planet we see today. This model was favored by many scientists because it aligned with observations of exoplanets and the composition of meteorites in our solar system. Core accretion also explained why Jupiter is so enriched in heavy elements compared to the Sun, as these elements would have been concentrated in the core during its formation. Juno's data showed that neither theory was quite right. Jupiter does have a core, but it is not a solid, compact ball of rock. Instead, it is diffuse, fuzzy, with heavy elements concentrated toward the center, but blending gradually into the surrounding hydrogen and helium without any sharp boundary. This fuzzy core is estimated to be about 10 times the mass of Earth, but it spreads out over a region roughly the size of our planet. The lack of a distinct boundary between the core and the rest of the planet suggests that the core has been partially eroded over time, with heavy elements mixing into the upper layers due to convection and other dynamic processes. This discovery forced scientists to rethink how giant planets form and raised new questions about the origins of our solar system. If Jupiter's core is diffuse and partially eroded, it implies that the planet has undergone significant internal reorganization since its formation. This could be the result of collisions with other planetary embryos during the chaotic early days of the solar system, or it could be a natural consequence of the enormous pressures and temperatures deep within the planet. Additionally, the fuzzy core challenges the traditional idea of a clear boundary between a planet's rocky interior and its gaseous envelope, suggesting that such distinctions may be more fluid than previously thought. Observation. Jupiter's winds extend more than 1,900 miles deep, interacting with the metallic hydrogen layer and influencing the planet's magnetic field. Interpretation. The depth of Jupiter's winds indicates that the planet's atmosphere is not a superficial layer, but a deeply integrated part of its structure, driven by internal heat and dynamic processes. Ether speculation. The fuzzy nature of Jupiter's core suggests that it may have undergone significant internal reorganization, possibly due to collisions or the natural evolution of its interior under extreme conditions. As Juno continues its mission, it will provide more data to help unravel these mysteries. The spacecraft's extended mission, approved through 2025, includes closer flybys of Jupiter's moons, particularly Europa and Io, which will offer new insights into the planet's gravitational field and its influence on these satellite worlds. By studying how Jupiter's gravity affects its moons, scientists hope to further refine their models of the planet's interior structure and better understand the processes that shaped and continue to shape this gas giant and its system. The depths of Jupiter are not just a scientific curiosity, they are a window into the history of our solar system. The planet's formation, its internal dynamics, and its gravitational interactions with its moons all contain clues about the conditions that existed in the early solar system and the mechanisms that gave rise to the planets we see today. As we continue to explore Jupiter, we are not just studying a single planet, we are piecing together the story of our cosmic origins. Part 7. The Fuzzy Core. What if Jupiter's core is not solid but diffuse? The answer to this question has reshaped our understanding of how planets form and evolve. Jupiter, the largest planet in our solar system, was long assumed to have a dense rocky core surrounded by layers of liquid metallic hydrogen and a vast gaseous atmosphere. But data from NASA's Juno mission, which entered Jupiter's orbit in 2016, revealed a far more complex story. The planet's core is not a small distinct sphere, but a sprawling, fuzzy region, where heavy elements like oxygen, carbon, nitrogen, and silicon are mixed throughout a zone spanning roughly 50% of Jupiter's radius. This discovery has forced scientists to rethink the fundamental rules of planetary formation. The discovery of Jupiter's fuzzy core was a turning point in planetary science. In the clean models, a planet should have distinct layers, a dense core, a liquid mantle, a gaseous envelope, each separated by a clear boundary. But Jupiter doesn't follow that rule. Instead, heavy elements like oxygen, carbon, nitrogen, and silicon are spread throughout a vast region spanning roughly half the planet's radius. These elements appear to have mixed with the surrounding hydrogen over billions of years. But how? The question is not just academic. Understanding Jupiter's core could provide insights into the formation of Earth and other terrestrial planets. If Jupiter's core is not a solid, well-defined sphere, it challenges the traditional notion of planetary interiors and suggests that the processes governing planetary formation are far more dynamic and chaotic than previously thought. One hypothesis suggests that Jupiter was hit by another massive object early in its history. A collision with a planet 10 or even 20 times the mass of Earth could have shattered a once solid core, scattering heavy elements outward and mixing them into the surrounding layers. Computer simulations tested this scenario, modeling thousands of impacts at different speeds and angles. These simulations showed that such a catastrophic event would have released an enormous amount of energy, equivalent to millions of hydrogen bombs detonating simultaneously. The shock waves would have rippled through Jupiter's interior, liquefying the core and dispersing its heavy elements into the hydrogen-helium envelope. However, the results were consistent. A giant impact would disrupt the core, but over time, gravity would cause the heavy materials to sink back down and reassemble into a compact core. The simulations couldn't produce a fuzzy core that stayed fuzzy for billions of years. So scientists turned to another explanation. Perhaps the fuzziness is original, a natural outcome of how Jupiter formed. In this view, as the planet accumulated mass, heavy elements didn't just sink and lock into place, they partially dissolved into the hydrogen and helium envelope, creating gradients instead of sharp boundaries. This process would have occurred during the early stages of the solar system, when Jupiter was still growing by accreting gas and dust from the protoplanetary disk. The intense heat and pressure within the young planet would have allowed heavy elements to dissolve into the surrounding hydrogen, creating a blurred, gradient-like structure rather than distinct layers. But how did these gradients persist? The answer lies in convection, or rather, the lack of it. On Earth, convection keeps the mantle churning, mixing material and spreading heat. If Jupiter's entire interior were convective, any compositional gradients would eventually be erased. But Juno's measurements suggest that large parts of Jupiter's interior are stable, meaning they don't mix efficiently. This stability allows the fuzzy core to persist, a testament to the complex dynamics at work within the gas giant. The data from Juno revealed that Jupiter's magnetic field is surprisingly uneven, suggesting that the planet's interior is not uniformly convective. Instead, there may be regions where heat is transferred primarily by radiation or conduction, which would prevent the mixing of materials and allow compositional gradients to remain intact. Observation: Juno's gravity measurements have provided unprecedented detail about Jupiter's interior. By mapping the planet's gravitational field, scientists can infer the distribution of mass within its layers. The data shows that Jupiter's core is not a small, dense sphere, but a vast, diffuse region. This region extends outward to about half the planet's radius, where heavy elements are mixed with hydrogen and helium. The gravitational signal is subtle but unmistakable. The core is not a distinct boundary but a gradient, with density increasing smoothly toward the center. This observation has forced scientists to abandon the traditional layered model of Jupiter's interior and embrace a more dynamic, nuanced understanding. Interpretation: the fuzzy core challenges the classical theory of planetary formation, which assumes that heavy elements sink to the center during the early stages of a planet's life. Instead, Jupiter's core suggests that the accretion process was messy and incomplete. Heavy elements may have been trapped in the hydrogen-helium envelope before they could sink to the center, or they may have been scattered by violent impacts. The fuzzy core also raises questions about the behavior of materials under extreme conditions. At the pressures and temperatures found in Jupiter's interior, heavy elements like oxygen and silicon may behave in ways that are difficult to predict. For example, they might dissolve into the hydrogen and helium rather than sinking to the core, creating the gradients observed today. Speculation: if Jupiter's core is fuzzy, it raises intriguing possibilities about the interiors of other gas giants. Saturn, for instance, may also have a diffuse core, though its smaller size and lower gravity might lead to different dynamics. Future missions to Saturn, Uranus, and Neptune could reveal whether fuzzy cores are a common feature of gas giants or unique to Jupiter. Additionally, the fuzzy core could provide insights into the formation of terrestrial planets like Earth. If heavy elements can dissolve into hydrogen and helium under extreme conditions, it might explain how rocky planets accreted the materials needed for their cores. The fuzzy core also invites speculation about the potential for exotic states of matter deep within Jupiter. At the extreme pressures found near the core, hydrogen may transition into a metallic state, while heavy elements could form unusual compounds or even new phases of matter. The fuzzy core is more than just a curiosity. It is a window into the violent and chaotic processes that shaped our solar system. As scientists continue to study Jupiter's interior, they are not just unraveling the mysteries of a single planet, but rewriting the story of how planets form and evolve. Each new discovery about Jupiter's core brings us closer to understanding the fundamental rules that govern the cosmos. Part 8. The Birth of Giants. What if fuzzy cores are the natural state of giant planets? Juno's discovery of Jupiter's fuzzy core raised a fundamental question. Is this feature unique to Jupiter, or is it a common trait among giant planets? To find out, scientists turned to Saturn, the next largest gas giant in our solar system. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, had collected years of data before its mission ended in a deliberate plunge into the planet's atmosphere. The spacecraft's final descent was a dramatic and poignant moment, as it transmitted data until the very end, ensuring that its 13-year journey would leave an indelible mark on our understanding of the ringed planet. Cassini didn't carry the same gravity-measuring instruments as Juno, but it had something else. Saturn's rings. These rings are not just beautiful, they are seismographs, recording vibrations inside the planet that ripple outward and disturb the rings, creating tiny waves that can be measured. The rings, composed primarily of ice particles ranging from microscopic grains to meter-sized chunks, act as a natural laboratory for studying Saturn's interior. Scientists pored over Cassini's data, analyzing the subtle oscillations in the rings to decipher the planet's internal structure. By studying these waves, scientists can probe Saturn's interior, much like seismologists use earthquakes to map Earth's core. When researchers analyzed Cassini's ring data alongside gravitational measurements, they found the same pattern. Saturn, like Jupiter, has a fuzzy core. Heavy elements are concentrated toward the center, but gradually blend outward without a sharp edge. Imagine a core that isn't a distinct solid boundary but a gradient, where the density of elements shifts smoothly from the planet's center to its outer layers. This discovery was a turning point. If both Jupiter and Saturn share this trait, it is unlikely to be a coincidence. Fuzzy cores may be a natural feature of how giant planets form, a revelation that changes everything we thought we knew about gas giants across the galaxy. The implications of this discovery are profound. If fuzzy cores are indeed universal among giant planets, it suggests that the traditional model of planetary formation, where a small rocky core forms first and then accretes gas, may need to be rethought. Instead, giant planets might form through a more chaotic, turbulent process where heavy elements mix with lighter gases as the planet coalesces from its protoplanetary disk. This idea aligns with the observation that many exoplanets, giant worlds orbiting distant stars, defy conventional formation models, with some orbiting surprisingly close to their stars or having bizarre compositions. Observation. The fuzzy core model could explain why some exoplanets, known as hot Jupiters, exist so close to their stars. Traditional theories struggle to account for how these gas giants migrated inward without being torn apart by tidal forces. A fuzzy core might allow for greater flexibility and resilience during migration. The birth of giant planets is a violent and dynamic process. In the early solar system, collisions between planetesimals, rocky and icy bodies, were common. These collisions likely played a key role in shaping the fuzzy cores of Jupiter and Saturn. Each impact would have mixed heavy elements into the growing planets, creating a blended gradient-like structure rather than a distinct layered one. This process may also explain the presence of heavier elements in the atmospheres of these planets, as the impacts could have launched material from deep within the core into the outer layers. Interpretation. The fuzzy core model also has implications for the habitability of exoplanets. Gas giants with fuzzy cores might have more complex internal dynamics, potentially leading to stronger magnetic fields. These fields could shield moons orbiting the giants from solar radiation, making them more hospitable to life. Speculation. Could fuzzy cores exist in smaller planets like Neptune and Uranus? These ice giants are smaller and have different compositions than Jupiter and Saturn, but their interiors remain mysterious. Future missions, such as NASA's proposed Uranus orbiter and probe, could shed light on whether fuzzy cores are a feature of all giant planets or limited to the gas giants. The discovery of fuzzy cores has opened a new chapter in planetary science. It challenges long-held assumptions and invites us to reimagine the birth and evolution of giant planets. As we continue to explore our solar system and beyond, the story of these cosmic giants will undoubtedly become richer and more complex. Part 9. The Polar Dance. Why do Jupiter's polar cyclones stay locked in geometric patterns? While Juno was revolutionizing our understanding of Jupiter's interior, its camera continued to capture images of the planet's surface, and the polar storms remained one of the mission's most enduring mysteries. At the North Pole, 8 cyclones surrounded a central vortex in a perfect octagon, each storm roughly the size of Earth, with winds howling at speeds up to 220 miles per hour. At the South Pole, 5 cyclones formed a pentagon around the center, their swirling clouds casting shadows across the volatile atmosphere. These storms have been stable since Juno's arrival in 2016, neither drifting nor merging, despite the chaotic nature of Jupiter's weather systems. The stability of these formations is made even more remarkable by the fact that Jupiter's atmosphere is the most turbulent in the solar system, with storms that can rage for centuries. Scientists have proposed several theories to explain the geometric patterns. One suggests that the cyclones are held in place by rings of anticyclonic winds, winds that rotate in the opposite direction, acting like barriers to keep the cyclones from drifting. These anticyclonic winds may act as invisible fences, maintaining the precise spacing between the storms. Another idea is that the cyclones are deep, extending thousands of miles into Jupiter's interior, rooted in convective flows driven by heat from below. If the cyclones were shallow, they should move with the surface winds. But measurements show that both the northern and southern storm patterns rotate much more slowly than the winds around them. At the North Pole, it would take roughly 100 years for the octagonal pattern to complete one full rotation, a glacial pace compared to the frenetic activity of the surrounding atmosphere. At the South Pole, about 50 years. This slow rotation suggests the cyclones are anchored by something deep inside the planet, but the details remain unclear. Observation: the polar cyclones are not uniform in size or intensity. The central cyclones at both poles are slightly larger and more powerful than their surrounding counterparts, perhaps due to their position at the axis of rotation, where they can draw energy from the planet's spin. The northern cyclones, in particular, exhibit subtle variations in color, ranging from pale blue to deep violet, which may indicate differences in temperature, chemical composition, or altitude within the storms. Interpretation: the color variations could be a result of upwelling ammonia or other compounds from deeper layers of the atmosphere. These compounds might interact with solar radiation, producing distinct hues that hint at the storm's internal dynamics. The larger size and intensity of the central cyclones suggest that they may be the primary drivers of the polar weather systems, influencing the behavior of the surrounding storms through complex atmospheric interactions. In July 2019, something changed. 2 of the southern cyclones began to move apart, and in that gap, a 6th cyclone appeared. For about 6 months, the southern storms formed a hexagon, a brief but significant disruption to the established order. The new cyclone was smaller and less intense than its companions, as if it were a fledgling storm testing the boundaries of the system. Then, as suddenly as it appeared, the 6th cyclone vanished and the structure returned to its original pentagon configuration. The event was a reminder that while the polar storms may seem stable, they are far from static. Their dynamics are governed by forces we are only beginning to understand, forces that could hold the key to unlocking the secrets of Jupiter's interior. Macro. Speculation. The appearance and disappearance of the 6th cyclone may have been influenced by a temporary shift in Jupiter's internal heat distribution or a localized disruption in the atmospheric flow. Such events could provide valuable clues about the mechanisms that maintain the stability of the polar storms. If similar disruptions occur in the future, they could help scientists refine their models of Jupiter's atmospheric dynamics and better understand the planet's deep interior. The polar cyclones are not the only storms on Jupiter, but they are unique in their persistence and geometric arrangement. Elsewhere on the planet, storms like the Great Red Spot are more chaotic and unpredictable, though no less fascinating. The Great Red Spot, a storm large enough to swallow Earth whole, has been raging for at least 350 years, but it lacks the symmetry and order of the polar cyclones. Its longevity may be due to its size and the sheer energy it contains, while the polar cyclones owe their persistence to their connection to deeper processes within the planet. The polar cyclones also differ from Jupiter's other storms in their isolation. While the Great Red Spot and other tempests are subject to the constant buffeting of the planet's banded winds, the polar cyclones exist in a relatively calm region at the top and bottom of the planet. This isolation may contribute to their stability, allowing them to maintain their geometric formations without interference from external forces. However, the exact nature of this isolation remains a mystery, as does the question of how deep the cyclones truly extend into Jupiter's interior. Observation. The poles of Jupiter are not merely sites of atmospheric activity, but also regions of intense auroral activity. The planet's powerful magnetic field funnels charged particles toward the poles, creating dazzling auroras that dwarf Earth's northern and southern lights. These auroras are visible in ultraviolet and infrared wavelengths, and their brightness fluctuates in sync with the planet's rotation. The interaction between the auroras and the polar cyclones is not yet understood, but it is possible that the storms play a role in shaping the auroral displays. 4. Interpretation. The auroras could be influenced by the electrical activity generated within the cyclones, as the storm's powerful winds and convective currents might create localized magnetic fields that interact with Jupiter's global field. Alternatively, the auroras might affect the cyclones by depositing energy into the upper atmosphere, altering the temperature and pressure conditions that govern the storm's behavior. As Juno continues its mission, it will gather more data on the polar cyclones, including high-resolution images and measurements of their magnetic and gravitational effects. Each pass over the poles brings new insights into these enigmatic storms, which remain one of the most intriguing features of Jupiter's dynamic atmosphere. With every piece of data, scientists move closer to solving the puzzle of the polar dance, a dance that has captivated them for centuries and continues to reveal the hidden workings of the solar system's largest planet. Part 10. The Moons of Jupiter. What secrets do Jupiter's moons hold? Jupiter is not just a planet, it is a system, orbited by at least 95 known moons. 4 of them, Io, Europa, Ganymede, and Callisto, are large enough to be considered worlds in their own right. Discovered by Galileo Galilei in 1610, these Galilean moons have long captivated scientists with their diversity and potential for harboring life. Together, these moons are more massive than all the other satellites in the solar system combined, making them a critical area of study for understanding planetary formation and the possibility of extraterrestrial life. During its extended mission, Juno flew close to 3 of these moons, revealing new insights into their unique characteristics. In June 2021, it passed within 652 miles of Ganymede, the largest moon in the solar system. Ganymede is a world of contrasts, with ancient, heavily cratered terrain alongside younger regions marked by grooves and ridges. It is also the only moon known to have its own magnetic field, generated by a liquid iron core. This magnetic field creates stunning auroras, much like Earth's northern lights, but invisible to the human eye, detectable only through ultraviolet observations. Ganymede's magnetic field also interacts with Jupiter's powerful magnetosphere, producing complex plasma dynamics that scientists are still working to unravel. In September 2022, Juno flew by Europa, the ice-covered moon believed to hide a liquid water ocean beneath its frozen surface. Europa's smooth, icy shell is crisscrossed by fractures and ridges, hinting at the dynamic processes at work beneath. Scientists believe that tidal forces exerted by Jupiter's gravity heat the moon's interior, keeping its subsurface ocean liquid and potentially habitable. This ocean, thought to be up to 100 kilometers deep, could contain more water than all of Earth's oceans combined. The moon's surface is constantly renewed by the movement of ice, with some regions showing evidence of recent geological activity, such as the formation of chaotic terrains where ice has melted and refrozen. But it was Io, the most volcanically active world in the solar system, that revealed some of Juno's most extraordinary discoveries. Io's surface is a fiery landscape of more than 400 active volcanoes, constantly reshaped by eruptions that spew lava and sulfur dioxide into space. The intense tidal forces from Jupiter's gravity, combined with the gravitational influence of Europa and Ganymede, generate enough heat to keep Io's interior molten. This constant volcanic activity releases vast amounts of sulfur and oxygen ions into space, creating a donut-shaped plasma torus around Jupiter that glows in ultraviolet light. The torus, discovered in the 1970s, is one of the most striking examples of how Jupiter's moons interact with the planet's powerful magnetic field. Observation. Juno's instruments detected changes in Io's atmosphere during its flyby, revealing how quickly the moon's volcanic gases are stripped away by Jupiter's magnetic field. The spacecraft's Jovian Infrared Auroral Mapper, GIRAM, captured the glow of Io's volcanoes, providing new data on their temperatures and compositions. Io's volcanic activity has profound consequences for the entire Jovian system. The moon's eruptions feed material into Jupiter's magnetosphere, contributing to the planet's intense radiation belts and auroras. These eruptions also leave deposits of sulfur and other compounds on Europa and Ganymede, altering their surfaces over time. The constant bombardment of charged particles from Io may even influence the chemistry of Europa's subsurface ocean, potentially providing energy sources for life. Interpretation. The data from Juno's flybys of the Galilean moons have deepened scientists' understanding of how these worlds interact with Jupiter and each other. Io's volcanic activity, Europa's potential for habitability, and Ganymede's magnetic field are all interconnected, shaped by the gravitational and magnetic forces of the Jovian system. These interactions offer a glimpse into the complex dynamics of planetary systems and the potential for life beyond Earth. Speculation. As researchers continue to analyze Juno's data, they may uncover new clues about the origins of the Galilean moons and their role in the evolution of the solar system. Future missions, such as NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, will build on Juno's discoveries, diving deeper into the mysteries of these enigmatic worlds. By studying these moons, scientists hope to answer fundamental questions about the habitability of icy oceans, the formation of magnetic fields, and the conditions necessary for life to emerge in the cosmos. The moons of Jupiter are not just celestial companions to the gas giant. They are laboratories for understanding the processes that shape worlds across the universe. From Io's fiery volcanoes to Europa's hidden ocean and Ganymede's magnetic field, these moons challenge our understanding of what it means to be a habitable world. As Juno continues its journey, and as future missions venture deeper into the Jovian system, the secrets of these moons will slowly come to light, illuminating the wonders of our solar system and beyond. Part 11. The Fires of Io. Could Io hold the key to understanding volcanic worlds? Io is a moon unlike any other. With more than 400 active volcanoes, its surface is constantly reshaping itself, covered in lava flows, ash plumes, and sulfur deposits that paint the landscape in vivid shades of yellow, orange, and red. The source of all this activity is Jupiter itself. Io orbits extremely close to the giant planet, just 262,000 miles away, closer than the Earth is to its own moon. As it travels around Jupiter, the moon's distance from the planet changes due to its slightly elliptical orbit, and with it, the intensity of Jupiter's gravitational pull. This constant kneading, combined with the gravitational influence of Europa and Ganymede, generates immense heat through tidal friction, melting rock deep inside Io and driving its endless volcanism. The energy produced by this process is staggering. Io radiates roughly 2.5 times more heat than it receives from the Sun, making it one of the most geologically active bodies in the solar system. Its lava flows can reach temperatures of up to 3,000 degrees Fahrenheit and travel at speeds of up to 330 feet per second. In December 2023 and February 2024, Juno made its closest passes of Io within 930 miles of the surface. Its infrared instrument, the Jovian Infrared Auroral Mapper, GIRAM, scanned the Moon's southern hemisphere, detecting something extraordinary: a massive volcanic hotspot larger than Lake Superior, spanning more than 40,000 square miles. The feature was emitting more than 80 trillion watts of energy, 6 times the total output of every power plant on Earth combined. Scientists had never seen volcanic activity this intense. The data revealed temperatures exceeding 1,600 degrees Celsius, 2,900 degrees Fahrenheit, hot enough to melt rock and create vast lava lakes. These lava lakes are not static, they are dynamic, with waves of lava overturning and spilling onto the surface, creating fresh deposits that can be tens of meters thick. The data suggests that the hotspot is not a single volcano, but several closely spaced eruptions happening simultaneously, possibly fed by a vast underground magma chamber. When Juno flew past Io again in late December 2024, it found the hotspot still erupting, with visible light images showing fresh lava flows and volcanic deposits. The discovery broke the previous record held by Loki Patera, a lava lake on Io measuring about 7,700 square miles. Loki Patera, named after the Norse god of chaos, has been observed periodically brightening and dimming over decades, indicating waves of overturning lava. However, the new hotspot dwarfs Loki Patera in both size and energy output, challenging scientists' understanding of Io's internal processes. The sheer scale of these eruptions means that Io's surface can change dramatically in just a few years, with entire plains of sulfur deposits shifting and reforming. Io's volcanic activity is not limited to its surface. The Moon's thin atmosphere, composed primarily of sulfur dioxide, is constantly replenished by volcanic outgassing. Plumes of sulfur dioxide gas and dust can reach heights of up to 300 miles, 500 kilometers, above the surface, creating a hazy, dynamic environment. These plumes are often associated with volcanic eruptions, such as the famous Tvashtar Paterae, where massive lava fountains feed towering columns of gas and ash. The material ejected by these plumes escapes Io's weak gravity and forms a torus, a donut-shaped ring of plasma, around Jupiter, contributing to the planet's complex magnetic field. This plasma torus is so dense that it glows in ultraviolet light, creating a faint but visible halo that stretches millions of miles into space. Juno will continue monitoring Io through the end of its mission, scheduled for September 2025. What scientists learn from this fiery moon could help them understand volcanic processes not just on other moons, but on rocky planets throughout the galaxy. Io's extreme activity offers a rare opportunity to study the dynamics of tidally heated worlds, providing insights into the internal structures of exoplanets and their potential for volcanic activity. For example, some exoplanets orbiting close to their stars may experience similar tidal forces, driving intense volcanism that could influence habitability. The intense heat and chemical reactions on Io could even produce unique organic compounds, though the moon's lack of liquid water makes it unlikely to host life as we know it. The Galileo mission in the late 1990s and early 2000s provided the first detailed glimpses of Io's volcanic activity, including the detection of more than 100 active volcanoes. One of its most dramatic findings was the observation of the Tvashtar Paterae eruption in 1999, which produced a plume that extended nearly 250 miles into space. The New Horizons spacecraft, which flew by Io in 2007, captured even more detailed images of these plumes, revealing their intricate structures and the way they interact with Jupiter's magnetic field. Each mission has added layers to our understanding of Io, showing it to be a world of constant upheaval and renewal. Observation. The immense energy output of Io's volcanic hotspots suggests that the Moon's interior is more dynamic and complex than previously thought. The presence of multiple simultaneous eruptions indicates a highly interconnected subsurface magma system, possibly fueled by a global magma ocean. The sulfur-rich composition of Io's lava and atmosphere also points to a unique chemical environment where volcanic processes are influenced by the abundance of this element. The bright yellow and orange hues of Io's surface are a direct result of sulfur and sulfur dioxide deposits, which can form intricate patterns as they cool and solidify. Interpretation. Io's volcanic activity is a direct result of Jupiter's gravitational influence, but the scale and intensity of its eruptions suggest additional factors at play. The Moon's composition, including its high sulfur content, may contribute to the explosiveness of its volcanoes. The ongoing eruptions could also be influenced by the interaction between Io's magma and its icy crust, which may act as a lid, building pressure until catastrophic release. The tidal forces exerted by Jupiter are so strong that Io's surface bulges in and out by as much as 330 feet during each orbit, generating friction that keeps the Moon's interior molten. Speculation. If Io's volcanic activity is driven by a global magma ocean, it raises intriguing questions about the Moon's formation and evolution. Could Io have once been a differentiated body with a molten core, or did its intense tidal heating cause its interior to melt over time? Additionally, the presence of such a vast magma reservoir could have implications for the habitability of other tidally heated moons, such as Europa or Enceladus, where subsurface oceans might interact with magma to create conditions favorable for life. The study of Io could also inform our understanding of early Earth, where intense volcanic activity may have contributed to the formation of the atmosphere and the emergence of life. Part 12. The Auroras of Jupiter. What generates Jupiter's powerful auroras? Jupiter's magnetic field fuels auroras far more spectacular than Earth's northern and southern lights. These auroras stretch hundreds of kilometers above the cloud tops, glowing with ultraviolet and infrared light, creating a mesmerizing display that dwarfs anything seen on our planet. Charged particles, accelerated by Jupiter's immense magnetic field, roughly 20 times stronger than Earth's, collide with atmospheric atoms at staggering speeds, releasing energy as light. With up to 4,000 electron volts, these particles create auroras that can outshine Earth's full moon from over 400 million miles away, a testament to the raw power of the gas giant. The scale of Jupiter's auroras is immense. Unlike Earth's narrow polar ovals, Jupiter's auroras cover areas larger than Earth's entire surface, stretching across vast regions of the planet's atmosphere. The main auroral oval, a glowing ring of light, is joined by transient features like arcs and spots, driven by the complex interactions between Jupiter's magnetic field, its rapid rotation, and the charged particles supplied by its moons in the solar wind. These auroras are not static. They shift and pulse, creating a dynamic light show that reflects the turbulent processes within Jupiter's magnetosphere. Jupiter's auroras are not solely triggered by the solar wind, as is the case on Earth. The planet generates its own charged particles, primarily from Io's volcanic eruptions, which spew sulfur dioxide and other gases into space. These gases are ionized by the solar wind and Jupiter's magnetic field, creating a plasma torus around Io's orbit, a donut-shaped ring of electrically charged particles. This torus, glowing faintly in ultraviolet light, fuels Jupiter's auroras, along with contributions from Europa and Ganymede. The resulting patterns are intricate and ever-changing, a cosmic dance of light and energy. Juno's ultraviolet spectrograph captured detailed images of Jupiter's auroras, revealing their complex structure in unprecedented detail. During close flybys, Juno detected whistlers, radio waves produced by the charged particles that fuel the auroras. These whistlers, when converted to audio, produce eerie, otherworldly tones that scientists use to study the auroral processes. By combining ultraviolet images with radio wave data, researchers have mapped the distribution of charged particles in Jupiter's magnetosphere with remarkable precision, uncovering the hidden mechanisms behind the auroras. Observation: Juno's data showed that Jupiter's auroras are highly dynamic, with features brightening and dimming over minutes or hours. This variability indicates unstable processes fueling the auroras, such as bright spots in the auroral oval corresponding to the positions of Jupiter's moons. These spots flare up as the moons pass through regions of enhanced plasma density, creating localized bursts of light that highlight the connections between the planet and its satellites. Interpretation: the rapid fluctuations in Jupiter's auroras suggest a turbulent magnetosphere, driven by the interplay between Jupiter's rapid rotation, completing a full turn every 9.9 hours, and the influx of charged particles from its moons. Magnetic reconnection, where field lines twist, stretch, and snap back together, accelerates particles to incredible speeds, generating the powerful auroras observed. This process is far more chaotic and energetic than anything seen on Earth, reflecting the immense scale of Jupiter's magnetic field. Speculation: if Jupiter's magnetosphere is as dynamic as the auroras suggest, it could influence our understanding of the planet's interior. The rapid rotation of Jupiter's core, which generates its magnetic field, may be affected by these turbulent processes. This connection could explain the extraordinary strength of Jupiter's magnetic field and how charged particles bombard its upper atmosphere, potentially influencing cloud and storm formation. The auroras may be a key to unlocking the mysteries of Jupiter's deep interior. Juno discovered that all 4 Galilean moons, Io, Europa, Ganymede, and even distant Callisto, leave auroral footprints in Jupiter's atmosphere. Each moon interacts uniquely with Jupiter's magnetic field, leaving its own glowing signature. Io's footprint is particularly bright, reflecting its intense volcanic activity, while Europa's is more subtle, hinting at its thin oxygen atmosphere. Ganymede, the only moon with its own magnetic field, leaves a complex footprint that reveals the intricate dance between its magnetosphere and Jupiter's. Even Callisto, the farthest of the 4, leaves a faint trace, a testament to its tenuous atmosphere. The auroras offer a window into the processes within Jupiter's magnetosphere. By studying their dynamics, scientists can learn about the interactions between Jupiter and its moons. The auroral footprints of the Galilean moons help map the magnetic field lines connecting the planet to its satellites, revealing the electrical currents that power the auroras. These currents, flowing along invisible pathways, transfer energy and matter between Jupiter and its moons, driving the auroras and shaping the magnetosphere. Beyond their beauty, Jupiter's auroras highlight the cosmos' complexity. As Juno continues its mission, it will uncover more secrets within the auroras, bringing us closer to understanding Jupiter's magnetic field and its interactions with the solar system. Each new observation adds to the story of Jupiter's auroras, revealing a world where magnetism, light, and motion intertwine in ways both breathtaking and profoundly mysterious. Part 13: The Great Red Spot. How deep does the Great Red Spot go? No feature on Jupiter is more iconic than the Great Red Spot, a massive storm that has been swirling in the planet's southern hemisphere for at least 350 years. This storm is not just a curiosity. It is a testament to the planet's tumultuous atmosphere, where winds can reach speeds of up to 400 miles per hour. The storm's winds complete a full rotation every 6 Earth days, a staggering display of velocity and force. When the Voyager spacecraft flew past Jupiter in 1979, the storm was large enough to fit 2 Earths inside, its crimson eye a stark contrast against the swirling clouds of Jupiter's surface. By the time Juno arrived in 2016, it had shrunk to 1.3 times the diameter of Earth, its once expansive form gradually contracting over the decades. The storm is still shrinking, but how deep does it go? Juno's microwave radiometer can peer through Jupiter's clouds, measuring temperature and composition at different depths. The data revealed that the Great Red Spot extends more than 200 miles into the planet's atmosphere, 50 to 100 times deeper than Earth's oceans. This depth helps explain why the storm has lasted so long. On Earth, hurricanes lose energy when they pass over land or encounter changing wind patterns. But Jupiter has no land, and the Great Red Spot draws energy from heat rising up from deep within the planet. As long as that heat source remains, the storm will continue, sustained by the relentless churning of Jupiter's internal dynamics. The storm's deep roots tap into a layer of the atmosphere rich in water vapor, which may further fuel its enduring power. The Great Red Spot is not alone in Jupiter's atmosphere. It is accompanied by smaller storms, known as white ovals, which are smaller but no less violent. These storms, while shorter-lived, often merge with one another, creating temporary but dramatic weather events. In 1939, 3 white ovals merged to form a single storm that persisted for decades, a testament to the dynamic and ever-changing nature of Jupiter's weather. The Great Red Spot, however, remains the undisputed king of Jupiter's storms, its size and longevity unmatched. Its red hue, thought to be caused by complex organic molecules, stands out starkly against the planet's banded clouds, a vivid reminder of the planet's chaotic and unpredictable nature. Observation. The Great Red Spot's shrinking size has been well documented, but its rate of contraction has varied over time. In the late 19th century, the storm was estimated to be about 40,000 kilometers wide. By the time Voyager 1 and 2 passed by in 1979, it had shrunk to about 23,300 kilometers. More recent observations by the Hubble Space Telescope and Juno have shown that the storm is now roughly 16,000 kilometers wide. This ongoing contraction has puzzled scientists, as the storm's longevity suggests it should be stable. Some researchers theorize that the shrinking may be cyclical, with periods of contraction followed by stabilization or even expansion. The Great Red Spot's internal structure is equally fascinating. At its center, winds are relatively calm, but as you move outward, wind speeds increase dramatically. The storm's edges are marked by chaotic turbulence, where winds collide with the surrounding atmosphere. This turbulence may play a role in the storm's shrinking size, as the outer edges of the storm are gradually eroded by the surrounding winds. Despite this, the storm remains a coherent structure, its core stabilized by the deeper layers of Jupiter's atmosphere. Infrared observations have revealed that the storm's core is cooler than its edges, suggesting that the storm's heat distribution may contribute to its stability. But scientists still don't fully understand why the storm is shrinking, or what drives its remarkable longevity. As Juno continues to study the Great Red Spot, it may reveal new insights into the dynamics at work within Jupiter's atmosphere, and the forces that shape the gas giant's weather systems. The storm's behavior could provide clues about the internal workings of gas giants, not just in our solar system, but across the universe. For now, the Great Red Spot remains one of Jupiter's most enduring mysteries, a swirling enigma that continues to captivate scientists and stargazers alike. Its deep roots and relentless energy make it a symbol of Jupiter's untamed wilderness, a storm that defies easy explanation and invites endless speculation. Part 14. The Bands of Jupiter. How deep do Jupiter's atmospheric bands extend? Jupiter's atmosphere is divided into dynamic bands, alternating stripes of dark orange and light gray called belts and zones. These bands are driven by winds exceeding 400 miles per hour, creating a spectacle of swirling clouds and storms that have captivated astronomers for centuries. Scientists have long debated their depth, as understanding it could reveal fundamental truths about Jupiter's internal structure and weather mechanisms. The bands are not merely superficial features, but are tied to the planet's immense internal energy. Early observations, including those from the Galileo spacecraft 1995-2003, hinted at the complexity of these bands but lacked the precision to measure their full extent. The Juno mission, launched in 2011 and arriving in 2016, was equipped with advanced instrumentation to study Jupiter's interior. Juno's design included a microwave radiometer to penetrate the cloud layers and a gravity science experiment to map the planet's gravitational field with unprecedented accuracy. Juno's gravity science experiment revealed that the bands extend roughly 1,900 miles below the cloud tops. At this depth, intense pressure transitions hydrogen from a gas to a liquid and deeper still to metallic hydrogen. This layer of metallic hydrogen is believed to generate Jupiter's powerful magnetic field, which is 20,000 times stronger than Earth's. Below 1,900 miles, Jupiter's interior rotates more uniformly than the chaotic storm systems above, suggesting a transition from the turbulent atmosphere to a more stable, cohesive interior. This discovery reshaped our understanding of gas giants. Jupiter's atmospheric flows penetrate thousands of miles into the planet, interacting with deeper layers in ways we are only beginning to understand. The belts and zones are integral to Jupiter's structure, connected to deep currents of liquid hydrogen and metallic hydrogen, and likely influencing its magnetic field. These currents could also explain the planet's intense auroras, which are the brightest in the solar system. Observation: the depth of Jupiter's bands suggests a link between atmospheric dynamics and the magnetic field. The metallic hydrogen layer, believed to generate the magnetic field, lies just below the bands. Changes in wind patterns could alter electric currents within this layer, affecting the magnetic field's behavior. For example, the Great Red Spot, a storm large enough to swallow Earth, has been observed to influence local magnetic field lines as it rotates. Interpretation: if the bands and magnetic field are connected, it could explain why Jupiter's magnetic field fluctuates. Observations of Jupiter's auroras, which brighten and dim with changes in the bands, support this link. These observations suggest a dynamic relationship between the planet's surface and its interior. Speculation: could this connection extend to other gas giants like Saturn, Uranus, and Neptune? Future missions with Juno-like instruments could test this hypothesis, deepening our understanding of gas giant interiors. Studying these planets in tandem could reveal whether the band magnetic field interaction is a universal feature of gas giants or unique to Jupiter. As Juno continues its mission, it will refine our estimates of the band's depth and structure. New missions, like the Europa Clipper, could provide additional clues about Jupiter's atmosphere and interior. In the coming decades, Jupiter will reveal more secrets, challenging our assumptions and expanding our understanding of gas giants across the universe. Part 15: The Search for Water. How much water does Jupiter's atmosphere contain? This question has perplexed scientists for decades, as water serves as a critical marker of Jupiter's origins and evolution. Measuring the amount of water in Jupiter's atmosphere was one of Juno's primary goals, as water is a key ingredient in understanding how the planet formed. If Jupiter accumulated most of its mass through gravitational collapse, it should have relatively little water, similar to the composition of the Sun. But if it formed through core accretion, building up from icy planetesimals, it should be water-rich, reflecting the icy material that helped construct its massive form. In 1995, NASA's Galileo spacecraft dropped a probe into Jupiter's atmosphere, venturing into the swirling clouds of the gas giant. The probe measured the composition of the gas as it descended, but the results were puzzling and incomplete. The atmosphere at that location was surprisingly dry, with far less water than expected, about 1/10 the amount of water found in the Sun. Scientists suspected the probe had simply entered an unusual region, a dry spot, or perhaps had sampled an area where water was bound in clouds or haze, hidden from detection. The Galileo probe's limited data left the question of Jupiter's water content unresolved. Juno's microwave radiometer was designed to overcome the limitations of the Galileo probe by measuring water content across much larger areas. The instrument could peer beneath the cloud tops and detect water vapor from a distance, providing a more comprehensive view of the gas giant's composition. The data confirmed that Jupiter's atmosphere is not uniformly dry. Near the equator, water is much more abundant than the Galileo probe detected, with concentrations roughly 3 times higher than the Sun's composition. However, the concentrations vary dramatically from place to place, suggesting that water on Jupiter is not evenly mixed. Instead, it is concentrated in certain regions, possibly linked to storm systems or atmospheric dynamics. The discovery solved the mystery of the Galileo probe. It had simply landed in the wrong place, an anomalous dry region near the equator. But it also raised new questions about how Jupiter's atmosphere circulates and how water moves through it. The distribution of water appears to be tied to the planet's powerful weather systems, including the Great Red Spot and other storms that churn the atmosphere. These storms may dredge up water from deeper layers, creating pockets of higher concentration. Juno's observations have also revealed that water is more abundant at Jupiter's poles than at its equator, hinting at complex global circulation patterns. Observation: Jupiter's water distribution is non-uniform, with higher concentrations near the equator and poles, and lower concentrations in mid-latitude regions. This pattern suggests that water is not well mixed throughout the atmosphere, and is influenced by dynamic processes such as storms and jet streams. The variations in water content have significant implications for Jupiter's formation history. If the planet formed through core accretion, the uneven distribution of water could reflect the uneven delivery of icy planetesimals during its growth. Alternatively, if Jupiter formed through gravitational collapse, the water distribution might be a result of later processes, such as the bombardment of comets and asteroids that delivered water to specific regions. Juno's ongoing measurements will help refine these theories. Speculation: the uneven distribution of water in Jupiter's atmosphere may be a fossil record of its formation, preserving the signatures of the icy materials that contributed to its growth. Alternatively, the water distribution could be a dynamic feature, constantly changing as water is transported and redistributed by storms and winds. As Juno continues to study the gas giant, it may reveal new insights into the processes that shaped its formation and the origins of our solar system. The spacecraft's extended mission, approved through 2025, will allow it to map Jupiter's water content in even greater detail, providing a clearer picture of the planet's internal workings and its role in the solar system's history. With each pass, Juno's instruments refine our understanding of Jupiter's atmosphere, bringing us closer to unlocking the secrets of the largest planet in our cosmic neighborhood. Part 16. The Legacy of Juno. What will be Juno's lasting impact on our understanding of Jupiter? Juno was originally designed to complete 33 orbits around Jupiter, enough to map the planet's gravity field, magnetic field, and atmospheric composition. But early in the mission, engineers discovered a problem with the spacecraft's main engine. Some valves weren't working as expected, and rather than risk a catastrophic failure, mission planners decided to keep Juno in its original 53-day orbit instead of shortening it to 14 days as planned. This decision, though born out of necessity, became a turning point for the mission, reshaping its trajectory both literally and figuratively. This extended the mission timeline significantly, but it also opened new opportunities. The longer orbits allowed Juno to explore the far reaches of Jupiter's magnetosphere and conduct close flybys of the Galilean moons. These moons, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each with unique characteristics that have captivated scientists for decades. Juno's extended mission has provided unprecedented close-up views of these moons, particularly Ganymede and Europa, which are believed to harbor subsurface oceans. During its flyby of Ganymede in June 2021, Juno captured the first detailed images of the moon's polar regions, revealing intricate patterns of fractures and grooves that hint at the moon's tectonic history. Similarly, its Europa flyby in September 2022 offered new insights into the moon's icy shell, which may hide a global ocean of liquid water beneath. NASA extended Juno's mission multiple times, first to 2021 and then to 2025. By September 2025, the spacecraft will have completed more than 50 orbits, far exceeding its original goals. This extension has not only increased the scientific output of the mission, but also inspired a new generation of researchers and engineers. Juno's data has fueled over 500 scientific publications, advancing our knowledge of Jupiter and its system. The mission has also engaged the public through stunning imagery, with citizen scientists processing raw data to create breathtaking visuals of Jupiter's swirling clouds and storms. These images have been shared worldwide, bringing the wonders of the solar system into classrooms, homes, and social media feeds. But Juno's legacy will be more than just the data it collected. The spacecraft has transformed our understanding of the largest planet in our solar system, revealing a world far stranger and more complex than we ever imagined. We now know that Jupiter's atmosphere is far deeper than anyone expected. Its core is diffuse and fuzzy, its magnetic field is complex and asymmetric, and its polar cyclones are locked in geometric patterns that defy explanation. The atmosphere, for instance, extends hundreds of kilometers deeper than models predicted, challenging long-held assumptions about gas giant interiors. The core, rather than being a solid, well-defined sphere, appears to be a diffuse mixture of hydrogen and helium, blurring the boundary between the core and the overlying layers. This discovery has forced scientists to rethink the formation and evolution of giant planets, not just in our solar system but across the universe. Juno's observations of Jupiter's magnetic field have been equally revolutionary. The field is not only stronger than expected, but also highly irregular, with regions of intense magnetic activity that defy simple explanations. These variations suggest that the dynamo generating the field is driven by complex flows of liquid metallic hydrogen deep within the planet. The polar cyclones, too, have puzzled researchers. Arranged in striking geometric formations, pentagons at the North Pole and hexagons at the south, these storms appear to be remarkably stable, persisting for years without merging or dissipating. Their origin and behavior remain one of the most intriguing mysteries uncovered by Juno. Yet for every answer Juno provided, it raised new questions that will drive the next generation of exploration and discovery. One of the most pressing is the nature of Jupiter's interior. How does the diffuse core influence the planet's gravity and magnetic fields? What processes drive the deep atmospheric flows that shape Jupiter's weather patterns? And how do these dynamics compare to those of other gas giants, like Saturn? Juno's data has laid the groundwork for future missions, such as NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, which will delve deeper into the Jovian system. These missions will build on Juno's discoveries, exploring not just Jupiter, but also its potentially habitable moons, where the search for life beyond Earth may finally bear fruit. Observation. Juno's extended mission has not only expanded our scientific knowledge, but also demonstrated the resilience and adaptability of space exploration. Despite technical challenges, the mission team found innovative ways to maximize the spacecraft's capabilities, turning a potential setback into an opportunity for groundbreaking science. Interpretation. The legacy of Juno extends beyond its scientific achievements. The mission has proven the value of long-term adaptive exploration, highlighting the importance of flexibility in space missions. By embracing unexpected opportunities, Juno has set a precedent for future endeavors, showing how even unforeseen challenges can lead to transformative discoveries. Speculation. As Juno approaches the end of its mission, it leaves behind a rich heritage of innovation and curiosity. Its discoveries will continue to shape our understanding of Jupiter and the solar system for decades to come, inspiring new questions and new missions. Perhaps one day, a future spacecraft will return to Jupiter, building on Juno's legacy to unlock even more of the planet's secrets. Part 17. The Future of Jupiter Exploration. What comes after Juno? Juno's mission will end in September 2025, but the exploration of Jupiter is far from over. The European Space Agency launched a mission called JUICE, Jupiter Icy Moons Explorer, in April 2023. It will arrive at Jupiter in July 2031 with a focus on Ganymede, Callisto, and Europa, the three largest icy moons. JUICE is equipped with 10 state-of-the-art instruments, including cameras, spectrometers, and radar systems, designed to unravel the mysteries of these moons. The spacecraft will spend at least 3 years orbiting Jupiter, conducting multiple flybys of each moon to study their subsurface oceans, geological activity, and potential habitability. Ganymede, the largest moon in the solar system, is of particular interest. It is the only moon known to have its own magnetic field, which may protect its subsurface ocean from Jupiter's intense radiation. JUICE will become the first spacecraft to orbit a moon other than Earth's when it enters Ganymede's orbit in 2034. This unprecedented feat will allow scientists to study the moon's interior, surface features, and potential for life in greater detail than ever before. Callisto, the second largest moon, is thought to harbor a subsurface ocean as well, though it lies deeper beneath the surface than those of Europa or Ganymede. Its ancient cratered surface tells a story of the solar system's early history, and JUICE will map its geology to understand how it evolved over billions of years. Callisto's lack of geological activity makes it a valuable point of comparison to its more dynamic neighbors, providing clues about the processes that shape icy worlds. Europa, the smallest of the 3 targeted moons, has long been a priority for astrobiologists. Its icy shell hides a global ocean of liquid water, heated by tidal forces from Jupiter. This ocean may contain the necessary ingredients for life, including water, energy, and essential chemicals. Europa Clipper, NASA's contribution to Jupiter exploration, will arrive in April 2030, conducting dozens of flybys to probe beneath its icy surface. Equipped with ice-penetrating radar, a magnetometer, and infrared spectrometers, Europa Clipper will search for plumes of water vapor erupting from the surface, which could provide direct samples of the subsurface ocean for analysis. These missions will build on Juno's discoveries, exploring the unique characteristics of Jupiter's moons and the potential for life within the system. Europa, with its hidden ocean, is a prime candidate for harboring life, and Europa Clipper will pave the way for future missions that might one day land on the moon and drill through the ice. Such a mission, still in the conceptual stages, could deploy robotic probes to explore the ocean directly, searching for signs of microbial life or chemical biosignatures. Observation. Jupiter's moons are not the only targets of interest. The gas giant itself remains a treasure trove of scientific discovery. Its dynamic atmosphere, powered by internal heat, creates storms and weather patterns unlike anything found on Earth. The Great Red Spot, a storm larger than our planet, has raged for at least 350 years, and its longevity remains a mystery. Future missions may study Jupiter's atmosphere in greater detail, using advanced instruments to map its chemical composition, winds, and temperature variations. Interpretation. By understanding Jupiter's atmosphere, scientists hope to learn about the planet's formation and evolution. The gas giant's composition reflects the conditions of the early solar system when the planets were first taking shape. Its enormous gravity well has preserved remnants of the primordial solar nebula, offering clues about the building blocks of our solar system. Speculation. Future missions may even aim to study Jupiter's interior directly. A proposed mission concept, the Jupiter Atmospheric Probe, JAP, would deploy a probe into the planet's atmosphere to measure its composition, temperature, and pressure at varying depths. Such a mission would face significant engineering challenges, as Jupiter's crushing pressures and intense radiation make it one of the harshest environments in the solar system. However, the scientific payoff could be immense, providing insights into the processes that shaped not only Jupiter, but also the gas giants orbiting other stars. But Jupiter holds more secrets than just its moons. The gas giant is a time capsule, preserving the conditions of the early solar system in its hydrogen and helium atmosphere. By studying its interior, scientists can learn about the processes that shaped our solar system and the forces that govern planetary systems around other stars. The coming decades promise to be a golden age of Jupiter exploration, as humanity's robotic emissaries unlock the secrets of this colossal world and its enigmatic moons. Part 18. The Final Countdown. What will be Juno's final act? Juno's journey will end as it began, with a fiery plunge into the unknown. In September 2025, the spacecraft's orbit will naturally degrade, pulled closer and closer to Jupiter by the planet's gravity. Its final trajectory will be meticulously calculated, ensuring that it avoids any of Jupiter's 79 known moons, particularly the potentially habitable worlds of Europa, Ganymede, and Callisto. Eventually, Juno will enter the gas giant's atmosphere, burning up in the same swirling clouds it spent years studying. The spacecraft, traveling at over 57 kilometers per second relative to Jupiter, will disintegrate within minutes, its components vaporizing under the intense heat and pressure of the planet's upper atmosphere. This is not an accident, it is intentional. Juno could still be carrying microbes from Earth, dormant bacteria that hitched a ride on the spacecraft during assembly in the clean rooms of NASA's Jet Propulsion Laboratory. Despite rigorous sterilization efforts, scientists cannot guarantee that the spacecraft is entirely free of Earth-based contaminants. If Juno were to crash into one of Jupiter's moons, particularly Europa or Ganymede, both believed to harbor subsurface oceans of liquid water, it could contaminate those worlds with life from Earth. Such an event could irreparably compromise future studies of these moons, which are prime candidates in the search for extraterrestrial life. To prevent this, Juno will be destroyed, following in the footsteps of NASA's Galileo orbiter in 2003 and Cassini at Saturn in 2017. This practice, known as planetary protection, is a cornerstone of responsible space exploration, ensuring that human endeavors do not inadvertently alter the natural evolution of other worlds. But Juno's legacy will live on. The data it collected has reshaped our understanding of Jupiter and the processes that govern gas giants across the galaxy. Its high-resolution images have revealed intricate storm systems, including the shrinking Great Red Spot, which has lost 15% of its width since the 1990s. Juno's magnetometer has mapped Jupiter's magnetic field with unprecedented precision, uncovering chaotic regions where the field lines twist and bend in ways that defy current models. Its microwave radiometer has peered beneath the cloud tops, revealing ammonia-rich plumes rising from deep within the planet's atmosphere. These discoveries have raised new questions and opened new avenues for exploration. Questions that will drive the next generation of missions to the outer solar system and beyond. As Juno burns up in Jupiter's atmosphere, it will leave behind a legacy of discovery that will echo through the halls of science for decades to come, a testament to human ingenuity and the relentless pursuit of knowledge. The spacecraft's final moments will be poignant as its instruments continue to transmit data until the very end. Scientists will analyze this last burst of information, hoping to glean insights into the composition of Jupiter's atmosphere, particularly the elusive layers of hydrogen and helium that make up the bulk of the planet. Juno's demise will also mark the end of an era, as it has been humanity's closest companion to Jupiter for nearly a decade. Yet its legacy will endure, inspiring future missions like NASA's Europa Clipper, set to launch in 2024, and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, scheduled for 2023. Another observation. Juno's final act is a reminder of the fleeting nature of human exploration. Each mission is a brief but intense window into the cosmos, a chance to gather knowledge before the tools of our curiosity are silenced. Juno's fiery end will be a bittersweet moment, a celebration of its achievements and a reflection on the impermanence of our presence in space. Barofrito speculation. As Juno disappears into Jupiter's storms, it is tempting to imagine what secrets it might uncover in its final moments. Could its instruments detect the faint signals of deeper atmospheric layers, or even the boundary where Jupiter's gaseous envelope gives way to a mysterious core? Such questions will linger long after Juno is gone, fueling the curiosity that drives us to explore further. Part 19. The Enigma Remains. Will we ever truly understand Jupiter? On a clear night, Jupiter is easy to spot, the brightest object in the sky after the Moon and Venus, a steady, unwavering point of light. Its brilliance is not merely symbolic, it is a physical testament to its enormity. Jupiter is more than twice as massive as all the other planets combined, a colossus that dominates the solar system with its gravitational influence. Through a small telescope, you can see its 4 largest moons, just as Galileo did more than 400 years ago. These Galilean moons, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each with unique geologies and mysteries. Through a larger telescope, you can make out the bands of clouds, the swirling storms, and maybe even the great red spot if conditions are right. This storm, larger than Earth, has been raging for at least 350 years, a testament to the planet's dynamic and turbulent atmosphere. But what you can't see is everything beneath. The metallic hydrogen ocean, a state of matter so extreme it can only exist under the crushing pressures deep within Jupiter, remains theoretical yet plausible. The fuzzy core, a diffuse region of heavier elements mixed with hydrogen and helium, defies our traditional understanding of planetary formation. The auroras flickering at the poles are the most powerful in the solar system, generated by the planet's rapid rotation and immense magnetic field. The cyclones spinning in perfect geometric patterns at the poles, each as wide as the continental United States, are a puzzle that challenges our comprehension of atmospheric dynamics. You can't see the 400 volcanoes erupting on Io, the most volcanically active body in the solar system, spewing sulfur and sulfur dioxide hundreds of kilometers into space. You can't see the subsurface ocean hidden beneath Europa's icy crust, a potential habitat for extraterrestrial life, nor the faint rings of dust that encircle the planet, sculpted by the gravitational tug of its moons. You can't see any of it, and yet it is all there, waiting to be discovered. Juno has given us a glimpse of a world far stranger and more complex than we ever imagined. Its precise measurements of Jupiter's gravitational and magnetic fields have revealed asymmetries and irregularities that contradict previous models. The spacecraft's microwave radiometer has peered beneath the cloud tops, mapping the ammonia-rich atmosphere and detecting the presence of water deep below. But the more we learn about Jupiter, the clearer it becomes how much we still don't understand. Every discovery points toward something deeper, something stranger, something we don't yet fully grasp. The unexpected clumpiness of the gravitational field suggests that the core is not a small, solid object, but a vast, diluted region, challenging our theories of planetary interiors. The enigmatic sprites and elves, brief, powerful bursts of lightning, hint at electrical processes unlike anything observed on Earth. And the persistent heating of the upper atmosphere, far greater than can be explained by solar radiation alone, remains an unsolved mystery. Observation. Jupiter's internal structure may be entirely different from what we thought. The traditional model of a small, rocky core surrounded by a thick layer of metallic hydrogen and a vast molecular hydrogen envelope may be too simplistic. Instead, the core might be a diffuse mixture of rock, ice, and hydrogen, extending outward much farther than expected. Speculation. If Jupiter's core is indeed fuzzy, it could imply that the planet never fully separated into distinct layers during its formation. This would challenge our understanding of how gas giants form and evolve, suggesting a more chaotic and dynamic process. And that is the beauty of science, the endless pursuit of knowledge, the eternal quest to understand the universe and our place within it. Each new observation, each unexpected result, is a step forward, a glimpse into the unknown. The Juno mission, with its 37 planned orbits and counting, has already rewritten the textbooks on Jupiter. Yet its findings have raised as many questions as they have answered, inviting future missions to delve even deeper. As Juno plunges into Jupiter's atmosphere, burning up in the clouds it spent years studying, it will leave behind a legacy of discovery and wonder. Its fiery demise, planned to prevent contamination of Europa or other potentially habitable moons, will mark the end of an era. But the data it collected will fuel research for decades to come, a testament to the enduring power of human curiosity. And as we look up at that steady point of light in the night sky, we will remember the spacecraft that dared to look beneath the surface and the questions it left for future generations to answer. For now, all we can do is watch and wonder what we'll find next. The next chapter of Jupiter exploration is already on the horizon. NASA's Europa Clipper mission, set to launch in the coming years, will investigate the icy moon's subsurface ocean and search for signs of life. The European Space Agency's JUICE mission will study Jupiter's magnetic field, atmosphere, and moons in unprecedented detail. And beyond these, future missions, perhaps even human expeditions, will continue to push the boundaries of our knowledge. Jupiter, the king of the planets, will remain a beacon of mystery and discovery, a reminder of how much we have yet to learn about the cosmos.